and welcome to Math World. Today we're going to talk about transformations. So transformations is just a way of moving a shape, but without changing the shape. So we want to talk about how can we take these different shapes, things that are used in blueprints maybe like a room or a house, without changing it. And maybe you wanted to relocate a room in your blueprint and you don't want to change the size of it. So you want to move it around. There's going to be 4 types of transformations we're going to talk about. Translations, reflections, rotations, and dilations. So the first one, translations, probably the easiest. In this case, we're going to move the shape left or right. So we're going to move it left or right. That's going to be along the x-axis. Or we can move it up and down. And that's going to be along the y-axis. So if you take this little triangle I drew here, and we look at its coordinates, we see that A has a coordinate of 2 and 3. And we see that B is at 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7. So this one's at 4 and 7. And C is at 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5. 8 and 5. So those are the coordinates of this triangle. And now I'm going to translate it by moving it. Now, the directions will have to give us a translation. Let's say there's a translation of x minus 3 and y minus 7. What that's telling us to do is to take all of your x values and subtract 3 from them, and take all your y values and subtract 7 from them. This shape is going to move 3 spaces to the left 3 and 7 spaces down the y 7. I'm going to take this little drag and drop and see if I can move the whole thing. So the goal is that the shape will not change. It'll simply go down 7 should be down 1, 2, 3, 4, 5, 6, 7, and then over 3, 1, 2, 3. It's going to drop me right here. And so you see this transformation, the whole thing just slid to the left 3 and down 7. Now I accidentally crossed out all my little axis bars here, so I don't know what they are, but actually I do, because I should have subtracted 3 from my x and 7 from my y. That means that my new A, and they usually put a little dash on it, A with the dash should now have coordinates of, let's see, my x value was 2, subtract 3, it's now negative 1. And my y was at 3, and I subtracted 7, so now it's at negative 4. That means this plot is at negative 1, negative 4, which it is. B with the dash, and I believe they call it prime, we'll call it B prime, means that, let's see, where should this one be? Well, 4 minus 3 is 1, and 7 minus 7 is 0. So this one's actually right at 1, 0. It should be right on the axis, right on the x-axis. And lastly, C prime should be 8 minus 3 is 5, and 5 minus 7 is negative 2. So my new coordinates would be 5 and negative 2, which it is. So a translation is just moving it left or right, up and down, and they show it in this type of transformation notation. Alright, so we move things left and right. Next, let's reflect. Now reflect's not too bad, because if I have a triangle, let's try to use the same one. The way I do a reflection is I'm actually going to use one of these axes, x-axis or y-axis, as the reflection line. And I'm going to mirror it over the axis. So let's say I want to reflect over the x-axis. Well, the x-axis is right here, running across left to right. So I want this shape to kind of go on the other side of the x-axis. Now I can't just grab it like I did with translations and move it down because it didn't flip over. Think about when you look at something in a mirror, it should be kind of the opposite. It's going to be upside down. So essentially I want this to go over the x-axis but also be upside down. So how can I do that? Well, the way I'm going to do is I'm actually going to count the spaces each plot is from the x-axis and then count that space again on the other side of the x-axis to get the new point. So let's take our A here. This A is 1, 2, 3 spaces from the x-axis. So let's count another 3 down. 1, 2, 3. That means new A should be right there. A prime is going to be right there. I'm going to repeat this. Let's see. B was 1, 2, 3, 4, 5, 6, 7 spaces. And now it'll be 1, 2, 3, 4, 5, 6, 7 spaces away. It's going to be all the way down here. So the closer the shape is to the x-axis, the closer they are to each other, while as I'm farther away, you see I get a farther reflection. And C is 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5 spaces on the other side, C prime. And now I get my shape. I'll connect the lines. And here's my same exact triangle. Remember, the goal is not to change the triangle. It's the same triangle, it's just upside down. You can kind of see how it's flipped over the x-axis. So it moved a little bit different than translation. It flipped upside down. Next we have the rotation. Now the rotation is probably the hardest because you want your shape to spin essentially around the axis as like it was a clock. So we'll use words like clockwise or counterclockwise. Now I could say I want you to do a rotation of 90 degrees clockwise, and you could try to take this shape and try to grab it, and 90 degrees would just be one spin. 180 would be all the way around here, 270 would be back here, and 360 is all the way around where it began. So you could try to take it and say, hey, it's about right there. But that's not going to work. That's not perfect. It needs to actually spin kind of like a rotation perfectly. The way we're going to do that is we're going to, let's see, we'll start it right here. We're actually going to take down the A, B, C measurements of this triangle. Now I have them up here, so I'm just going to borrow them from right here. So my ABC of this triangle is these coordinates. So once you have your ordered pairs, let's label them A, B, and C, and we know what they are, we're then going to actually take the whole paper and rotate the paper. So imagine you're taking your paper at home, and you're actually going to turn your whole paper. Now I'm going to rotate mine to the left. I'm actually going to rotate the opposite direction I want my rotation. So if my rotation is 90 degrees clockwise, which is the right, I'm going to turn my paper to the left, turn it the other way, and then I'm going to plot these ordered pairs that I kept over here. Remember I kept them? I'm going to put them as if I was plotting them normally. So I'm going to put an A at 2 and 3. A is at 1, 2, 1, 2, 3. B is at 4 and 7, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7. There's my new B, B prime. And C is at 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5. It's out here. So I'm going to plot my new letters, and then I'm going to connect these because it's going to create the exact same shape. A, B, and C they're all exactly the same distance from each other. However, once I'm done drawing it there, I'm now going to take my paper and rotate it back the way it was. So I'm going to rotate the paper back right 90 degrees. And look, there's my original triangle, and my new triangle is now down here. See how I drew it? I rotated my paper, drew the new triangle, and then put my paper back the way it was originally. Now this original triangle has been rotated 90 degrees. And look, not only did it land down here in this new quadrant, but you see it's kind of been shifted a little bit too. You can kind of see it's spun. It's spun around the origin. And that's a rotation. And so using this kind of turn paper method is the easiest way to do it. Keep track of your ordered pairs. And I can do that for any of them. I could rotate this 90 degrees. I could rotate it 180 degrees and plot my new triangle here and turn it back. I can do 270 to go all the way around. It won't matter. I can do this same trick. Alright, the last one is dilation. Now dilation is slightly different than the rest. All the other transformations, rotation, reflection, and translation, they move the shape without changing the size at all or the shape. Now a dilation, the shape is not going to change, but the size will. I'm going to make it bigger or smaller. Now what I'm going to do here is I'm going to take the ordered pairs that I have. It's always important to know your ordered pairs. And I'm either going to make them smaller or bigger. So usually a dilation is kind of like a scale factor. It'll say something like dilation times 2. Alright, so I'm going to take each of my original ordered pairs and get a new plot. A prime will be at 2 times 2 is 4, and 3 times 2 is 6. So my new A will be at 4 and 6. There's my new A. The new B prime, will be at 8 and 14. Now this one's going to be off the map. Let's see, 4, 8, there's 7, 8, 9, 10, 11, 12, 13, 14. We'll just say it's up here. But normally I would count right along the axes. So there's B prime. C prime is going to be at 16 and 10. 8 times 2 and 5 times 2. So it's going to be at 16. It's way out here. And 10, which is up here. So look what happened with the dilation. When I do a dilation, it keeps the exact same shape. They always keep the same shape, but the size got bigger. The size actually got larger. So it dilated by a factor of 2. This new larger triangle is twice as large as the smaller triangle, yet exactly the same shape. Same shape. They all have the same shape. Now what does that mean about same shape? That means we know that if angle B is 40 degrees on B prime, then the other angle B must also be 40 degrees. And we can kind of do a little angle math there, that the angle should always be the same because it's the same shape. Alright, so there's dilations. Now we can do dilations. Also, one last thing with dilations is you can get smaller. You can do times a half. And all of these ordered pairs in the original would get halved, and we'd have a much smaller triangle. It would be down here somewhere, wouldn't it? It'd be a tinier triangle. So you can dilate to get bigger or smaller. Rotate clockwise or counterclockwise. Reflect over the x-axis or the y-axis. Now y-axis would be this axis, and we'll put our reflection somewhere over here. I'm just going to guess it would look something like this. See how it still has kind of a mirrored shape? And lastly, translations, left, right, up, down. Transformations. Well, that's it, and I'll see you in class. Hey class, Mr. Bigsby with the hat. And here's your challenge question for transformations. If we start with figure A right here, this triangle, and I use 2 transformations to turn it into figure B down here, which two transformations did I use? So go back and look at the 4 we just learned and see how did I get it from this figure from A to B. Leave your answer in the comments. Later. Now for a word from our sponsor, Paper Cut Games. This week's game is Patchwork. Patchwork's a cool little 2-player game. It's about building a quilt, but it's kind of like playing Tetris, and it's really fun. Essentially, in this game, there's going to be a bunch of quilt pieces that are kind of all scattered around. And I'll show you down here the game board. There's all these quilt pieces that you're going to try to get onto your game board and build your perfect quilt where it doesn't have any holes. And whoever can do that the best usually wins. Now, it's not that simple because you have a choice on your turn of what you want to do. You can either A, try to get buttons, because buttons are your money, they're your currency. You don't always have buttons to buy things. So you can get buttons, or on your turn, you can spend the buttons you do have to try to buy a piece. And the piece will tell you how many buttons it costs. This one costs 10, it's a pretty good piece. And you would pay for the buttons and then put them onto your quilt and hopefully put it somewhere that makes a good spot. Also, what's kind of cool about this game is the pieces also cost you movement spaces. This thing says you move 3 spaces forward. Moving forward in this game is actually bad. If you look at the game board in the background, you see the green piece is moving around the game board. If you get to the end, you actually end your game. The game's over. So you want to try to buy as many pieces as you can before you get to the end of the game. You want to kind of not go so fast. And as the game moves around, you're buying the pieces and building it up. And it's a really simple game, yet a lot of fun to kind of figure out, oh man, where should I put these pieces? Or do I want to buy this, or do I want to save my money for a bigger, better piece later down in the game? Ooh, this crazy piece. And so it's a fun little quilt game. That is Patchwork. I'm Mr. Bigsby, and I approve this message.